Hello everyone, my name is Praveen. My roll number is 450, ECE Department, VVIT University. My topic is ergodic process, autocorrelation and cross correlation, understanding the statistical properties and temporal relations within ergodic process through correlation analysis. Introduction to ergodicity. An ergodic process possesses a fundamental property. Its statistical characteristics can be inferred from a signal sufficiently long time series observation. This means the time average equals the ensemble average, allowing researchers to understand the process behavior from one realization rather than requiring multiple independent samples. Ergodicity is crucial in signal processing, economics, and physics. It ensures that measurements taken over time provide reliable estimates of process properties. A process a process must satisfy stationarity, where statistical properties remain constant over time as a prerequisite for ergodicity. Stationarity, statistical properties constant in time. Mixing, independent from distant past events. Ergodicity, the time average, ensemble average. Importance of correlation in analyzing ergodicity process. Correlation analysis forms the foundation for understanding temporal and cross variable relationship in ergodic processes. These measures quantify how values at different times or between different variables relate to one another. For ergodic process, correlation functions reveal memory effects, how past value influence future behavior. Autocorrelation identifies patterns, periodicities, and lag structures within a single series. Cross correlation uncovers dependency between two processes, enabling prediction and control. Together, these tools provide comprehensive insight into process dynamic and dependencies, essential for modeling, forecasting, and system identification. Memory detection. Memory detection reveals how historical values persist in current behavior. Dependency qualification measures strength and direction of relationships. Pattern recognition, forecasting enhancement. Forecasting enhancement improves predictive models through lag identification. Now, autocorrelation functions ACF. Interpreting the plots. The autocorrelation functions the measures the correlation between a process and itself at different time lags for an ergodic process x of t. The ACF at lag k is defined as rho of k is equal to covariance of x of t comma x of t plus k. Variance of x of t. Variance of x of t. ACF plots display ACF plots display ACF plots display the correlation values against lag numbers. Keyframes include include values between -1 and +1, decay patterns, decay patterns memory length, and significance bounds. Typically, typically plus 1.96 by root n, showing statistical significance. Rapid decay suggests short-term memory wishlist. Slow decay indicates long-range dependence. Peak at regular intervals. Intervals reveal properties. Periodicity. Interpreting ACF plots. Sharp cutoff. Moving a average process. Exponential decay. Autoregressive process. Slow decay means non-stationary for long memory. Next, regular peaks means seasonal pattern. Seasonal patterns. Practical insights. Practical insights. Confidence bands identify significant lags. Next one, negative correlations suggest mean reversion. Zero autocorrelation indicate independence. Next, spikes reveal important time scale. Correlation examining relationships between two ergodic processes. Cross correlation quantifies the relationship between two distinct ergodic processes, x of t and y of t, are different time lags, unlike autocorrelation, which examines one process. Cross correlation reveals how one process influences or relates to another. The cross correlation functions at lag k is defined as rho of xy of k is equal to covariance of x of t comma y of y t plus k by root over variance of x of t into variance of y of t. The analysis identifies leading and lagging relationship. May maximum at positive lag indicates x leads y at negative lag. Y leads x cross correlation ranges from -1 to +1, with value near 0 indicating independence between processes. Lead lag detection identifies which process precedes the other. Dependency measurement quantifies strength or inter-process relationship. Synchronized analysis reveals temporal alignment ergodic process. Cross-correlation functions (CCF) identifying learning lagging relationship. Cross-correlation functions plots displays the strength of relationship between two processes time different lags across different time lags. The axis represents lag. The axis represents lag, positive, 0 or negative. We list the y-axis shows correlation magnitude. Confidence bands indicate statistical significance, typically set at plus or minus 1.96 by root over n. Critical interpretation features. The lag at maximum correlation reveals the optimal time shift between the process. Positive lags mean the second variable leads. Negative lags means the first leads. The magnitude of peak correlation indicates relationship. Strength asymmetric patterns reveal directional causality essential for understanding causal dynamics in coupled systems. Zero lag peak. Process occurs simultaneously with strong correlation. Negative lag peak. Second variable anticipates or precedes first variable. Positive lag peak. Second variable responds after After first variable changes, multiple peaks, multiple peaks, complex dynamics with multiple interaction path, practical applications, autocorrelation and cross correlation in real world scenarios. Correlation analysis of ergodic process serves critical functions across multiple disciplines in financial markets. Autocorrelation detects mean reversion or momentum in stock prices, which cross correlation identifies relationship between different assets for portfolio optimization. In climate science, autocorrelation reveals atmospheric cycle and memory effects in temperature data. Cross correlation links precipitation to atmospheric pressure patterns. Signal processing applications includes noise filtering, system identification, and fault detection. In neuroscience, cross correlation reveals connectivity between brain regions. Environmental monitoring uses these methods to track pollutant transport and ecosystem dynamics. Quality control employs autocorrelation to detect process shifts and degradation patterns. Financial markets detecting trends and asset relationships for trading strategies. Environmental science, understanding atmospheric cycles and climate patterns, signal processing, filtering noise and identifying system characteristics, medical diagnosis, analysis, biomass, neural. Thank you. Now, key takeaways. Ergodic process allows temporal analysis for universal insights. Autocorrelation reveals process, memory, and internal structure. Cross-correlation uncovers relationship between process. Both tools enable forecasting, control, and system understanding. Next steps. Apply these correlation techniques to your own data sets. Analyze autocorrelation pattern to understand process dynamics. Use cross-correlation to identify relationship and causal structures in coupled systems. Thank you.